then next week, we're going to start showing you some of the advanced tools that you can use with your models that you've been making. This is what you could consider post-processing of the models that you've produced. So today we're going to talk about motion analysis and photo rendering. Next week we're going to talk about two other more advanced kinds of analysis, those being CFD and FEA. Okay? So motion analysis is what you would expect. We can animate distantly and we can analyze this motion to determine things like velocities, accelerations, displacements, forces, and other parameters. The photo rendering lets us take the rasterized models like you've been used to looking at in SolidWorks graphics and turn those into something that looks a whole lot more like an actual photograph of the part. So you can produce some really nice graphics of your models and everything. Now before we start these two topics though, I do want to show you one trick, or give you one hint that can give you a much nicer result anytime you want to simply take a screenshot of your model. So, and many of you did this for your proposals, for the final project. Probably all of you will want to do this for your final report. You'll have models, you'll want to put pictures of those models into your report to talk about them. Now, I like to use the Microsoft snipping tool to do screenshot. How many of you are familiar with the Microsoft snipping tool? Okay, a few of you are. If you're not, this is a really handy tool to be familiar with. So let me go ahead and show that to you. It has nothing to do with SolidWorks. This is just part of the standard Windows environment. It's a Microsoft application. But anyway, if you're not sure where to find it, just search in your program, search for the word snip, and it'll come up. So click the snipping tool, and this allows you to simply draw a box around whatever you want on your screen, and it will save that image. You can save it as a picture file, or it's currently copied to the clipboard, so you can just paste it right into a document, like a Word or PowerPoint document. But using the default SolidWorks environment, that background, you get this annoying gray shading that just doesn't look so good, right? It kind of detracts or distracts from the model itself. It would be really nice if we could get rid of that gray shading in the background, but I'm going to show you the easy way to do that. In SolidWorks, okay, this and the View Display buttons, this button right over here that says Apply Scene, if you click the drop down, you have a whole bunch of different backdrops that you can use. One of them is called Plain White, and that gets rid of that shading that we had before. So now if we do a snip of that and paste that into Microsoft Word, side by side. Okay, if you were putting these into a report or even into a PowerPoint presentation, in my opinion, I think this one that has the plain white background looks a whole lot more professional than this one. So I would encourage you to always go to that plain white background. And of course, if this was in a PowerPoint slide, you could set white to be a transparent color, and then you just have your background showing through, and all you would see is the bottom. So that's a hint for being able to get a nicer looking screenshot from SolidWorks. Okay, so let's see. Get rid of that and open up. Okay, so now we're ready to start motion analysis. Both of these two tools actually are sort of add-in packages that are not part of the base SolidWorks package. Now they are included in the academic version, and I'm pretty sure they are included in the student version as well. If you use the student version, you probably have these industry and you want to use it, they're going to charge you several $1,000s more for this extra capability. But the first thing we need to do is actually activate these two tools in SolidWorks. So what you will do is go up to the Tools menu and go all the way down to the bottom of that long menu and choose Add-ins right here. Okay, and that brings up this box of a whole bunch of those advanced packages that you can add in. The ones that we want for motion analysis, we want this SolidWorks Motion right here. So I'm going to put a check mark next to it. And for the photo rendering, we're going to use Photo 360. So I'm going to go ahead and put a check mark next to it. So checking them on the left will add functionality to your current session of SolidWorks. If you check it on the right, it's going to load that functionality every time you start SolidWorks, which will make the time to load SolidWorks quite a bit longer. So generally it's better to just add them when you actually want to use them in a particular session. Don't choose to do them every time on startup. We'll accept that. Okay, so the situation we have here is, this is for our motion analysis. So this is the little egg landing vehicle, and it's going to drop down under Moon's gravity and land on the landing pad down here. And we want to, our goal is to design a good suspension system for the egg so that it doesn't have a rough landing. Okay, so to access motion analysis, what we do is click on this little tab at the bottom that says Motion Study 1. Okay, that tab has been sitting there. We've been ignoring it all semester long. We're going to use it today. We click Motion Study 1. And by default, it's going to come up set to simply animation. Okay, you've got three options here for the type of study. You can do an animation, which is just going to animate and show movement using the assembly makes that you've created. Okay, or you can do a basic motion study, which gives you a little bit more capability. You can add springs, gravity and motors. But the full-blown version is the motion analysis. That's where you can add all different kinds of, motors, springs, dampers, contact, and you can get results that show numerical values. So we're going to do motion analysis. Now, if you only see these first two options, that means you forgot to go up and turn on the add-in in the tools menu. You need to go add in the motion package. But we'll go to motion analysis. And so we've got this little timeline down here. This just relists pretty much all the parts that were in our assembly. And by the way, this assembly is something you can download from D2L. It's all provided for you. Okay. And so we've got the egg positioned up here at the top. If you want to just create an animation like a movie file, you can do that just by establishing different orientations and camera views. You can create keyframes here just by if we enable that. And like, suppose I wanted it to start in that position, I would just click here. Let's see. Like that. Well, anyway, I should have practiced that more before I started talking about it. But you can create keyframes. How many of you have created movie files before where you... Okay, so this is the same kind of thing. You just position the zoom or the orientation the way you want, click on the timeline to put that keyframe there, and then you can move it to a different orientation or zoom out or zoom in, click on the timeline to place that keyframe, and SolidWorks will kind of interpolate between those different views that you've defined to create a smooth animation. Okay, so that's not really what we're interested in today. We want the motion analysis capability. So we've got this button right here is the calculate button. Every time we define a change in the motion study, we change the setup, we're going to hit the calculate button to recalculate this new scenario. Okay? Now after you calculated it, you can hit the replay button just to replay what's already been calculated. Okay? And you've got some buttons over here where you can define different things like motors, springs, dampers, contact, gravity. So to get started, we've opened up the assembly. If we hit the calculate button right now, okay, you can see it starts to calculate, but we have no motion, nothing's happening. And that's because we haven't defined any forces or contact or anything that would cause motion to happen. So the first thing we need to do is add gravity. We do that by going to this little button that looks like an apple and it says gravity. Hit that button and we can type in, we can choose the direction gravity should act in. So in this model orientation, we want gravity to be in the Y direction. So we'll choose Y and we give it a value here. I think Moon's gravity is 1.62 meters per second squared, I believe. So I'm just going to type that in, 1.62 meter per second squared. Hit enter, it converts it to inches per second squared, that's fine. Click the check mark. Okay, so now we've got gravity defined here, and it's added to our little motion analysis model tree right here. And if we calculate again, now we see the egg starts to fall, but it goes right through the moon and all the way down. So now we need to define contact. Drag this back to the beginning. So we use this button that kind of looks like a little cam to define contact. Click on that, and we want solid body contact. And we're going to select the bodies that SolidWorks should check for contact between. So that's going to be the surface of the moon, and each of the 3 legs of the egg, and the egg itself. Because we want to find out if the egg actually bangs into the surface of the moon. That's what we're trying to prevent. Okay. You can define materials here. We don't need to. We're just checking for contact. So we'll say OK.
Little rubber ball mounts.
Let's see. In this mode of analysis, yes, it will. Because you can also specify coefficients of friction for the material, so it will include the effects of friction, and you can include elastic properties. So yes, you could define realistic bouncing motion. Yeah. Okay. So let's see, we've got, okay, so let's see what happens now. Now if you, a common mistake people make here is, again, they just hit the play button, but remember, that's just going to replay what it's already done. So you're not going to see any change take effect from the contact that we just defined. It goes right through the moon again. When you see the gray crosshatch here on the timeline, does that show up? A little bit. That is a hint that you need to recalculate in order to update your results. Okay, so we'll go back and do recalculate. And let it fall. And it just kind of squats there. Still moving around a little bit, but there's nothing there that would make a good suspension system. We've got linkages. There's no spring forces or dampers, so it really is not going to absorb impact. It's just going to let the egg kind of smash into the ground. It should be coming down here again, like that. You can see the legs actually bounce, recoil a little bit. Okay, so to make this a good suspension, let's add some springs. We've got a button for adding springs right here. It says add a spring between components. So go back to our egg, and what we want is, well, you can do linear or torsional springs. This is going to be a linear spring. We're going to select the surfaces that the spring acts between. So it's going to act between that face and that face up there. Okay, and it gives you a visual representation. And that's like the Arnold Schwarzenegger version of a spring. We can make that look a little more realistic for our application if we scroll down here to where it says display. Okay, we can set in, let's try for the coil diameter, let's say 0.2, number of coils 5, that's fine, but let's make them a little smaller for the wire diameter, let's say 0.05. So that looks a little more reasonable. Okay, but that change did not affect the physical properties of the spring. That was only changing the way it's displayed on the screen. To control the physical properties of the screen, we go back up and change the spring parameters, like the spring constant K or the exponent. You know, in statics and other physics and other courses, you probably work with springs, right? Springs produce force that is proportional to what?
Displacement.
To displacement, right. If you've got a spring and you compress it 1 inch and it gives 5 pounds of force, you compress it twice as much, it's going to give twice as much force. Well, that's if you're working with a linear spring that has a coefficient and an exponent of 1. But in SolidWorks, you can define much more complicated springs. Okay? You can do nonlinear springs. For now, we'll just stick with linear. We'll give it a K value. Again, that's the spring constant is how many pounds of force it will produce with a given increment of displacement or deformation. So this is 1 pound per inch. We'll stick with that. This is the unsprung length, or the free length of the spring. And that's saying, okay, when you put this spring into position, is it already squeezed down so that it's like loaded and ready to spring something off? Or is it stretched out so that it's actively pulling on whatever it's supporting, whatever it's connected to? Or by default, it's going to go in and use that link between those surfaces I clicked on to be the unsprung link, which means it's not loaded. It's just in a passive condition in there until something then compresses it or extends it. Okay, so let's accept that for the first spring, and we need to simply repeat that same process for the other legs. It saves some of our settings, so we can just click the new surfaces. For that one to act between, it saves the display settings and the value of K. We'll say OK, and then do it for this last leg. Spring from there to there. Okay. Now, unless I accidentally did one leg twice, we should have one. Okay, looks like we've got one spring on every leg. So let's get back to a good view and recalculate it. Calculate button. Okay, now it bounces. And it keeps bouncing. And it just keeps bouncing. Because these are pretty much ideal springs. There's very little, I don't know if SolidWorks is calculating any dissipative losses in the springs. I think they're just considered ideal, so it would bounce forever if I let it run forever, probably. But just for fun, before we go in and add some damping to make this a bit more realistic, let's change one of the springs to a different spring constant. So I'll go to Edit Feature. Let's make it 10 pounds instead of 1 pound.
Only one?
And let's calculate that. Okay, so it comes down and okay, so that's not going to be very good now. Completely over. Okay. So that's not a good suspension system. That's just totally broken. But, and your goal in the homework is to design a good suspension system. But you can certainly have some fun playing with it before you choose your final design. Okay, so to stop it from just bouncing over and over and over, the physical mechanism that would prevent that is what? friction. And if you wanted to create extra friction, what kind of mechanism would you use? Like on a car, what prevents the car from just bouncing over and over and over after you hit a bump? The suspension, and within the suspension is the shock absorber, right? So we have a button here for creating a damper, which is the shock absorber. Okay, but because most springs have inherent damping, we don't have to add a separate shock absorber using this button. We can just go back and edit our spring definition because it's got a section in it right here for adding damping. Okay. So we click the checkbox to turn on the damper, and again, you can choose a linear or a nonlinear damper. We'll stick with linear for now. And let's just give it a damping value of, let's try 0.05. Okay. Let's give that a try, and I'll do the same thing for the other two springs. 0.05. Okay, so now we said that a spring creates force that is proportional to displacement. A damper or a shock absorber creates force that is proportional to what?
Mass?
Not mass.
Acceleration.
Close. It's actually proportional to velocity. Okay. So it creates frictional or resistive force that's proportional to velocity. And that's a good short answer question that can come up on the final exam. So make a note of that. Spring creates force proportional to displacement. A damper or shock absorber creates force that is proportional to velocity. And if we look at the way it was defined, you can see that in the units itself, like this coefficient C has, I put in a value of 0.05, but its units are pounds force per inch per second. Okay, so the faster this thing hits, the greater the force is that is dissipated. Okay? Water is a really good fluid that mimics a damper. Like if you jump off the diving board and belly flop on the surface of a swimming pool, that hurts because you're going so fast it creates a lot of force. Whereas if you're walking through that same swimming pool at a slower rate, you can walk and it doesn't create nearly as much force because the force is proportional to the velocity or the relative velocity between the objects. So, okay, so we've got our springs defined. Let's go ahead and calculate this now. Zoom in a little bit. Okay, so it bounces and fairly quickly it damps out. Zoom in a little bit more on the landing, and let me just play that one more time for you so you can see how it. So you can compare that with what we had as motion without the damper. Here it comes. It looks like it hit the ground, so that's not good. But like 1.5 or 2 bounces, and it's pretty well damped out of that point.
Can you have it light up if it does hit the ground, or can you do some kind of detection where you're not just kind of looking at it and saying, oh, it kind of looks like it does?
Well, we can tell if it hits the ground by looking at a plot of the acceleration, which we'll do next.
Okay.
Let's see if there's anything I've left out that we want to talk about. So I think the next thing we're ready to do is actually make some plots of the results. Because you see these are the parameters that you will play with to get a good suspension. And your goal is to get a suspension that doesn't let the egg hit the ground. But also, your goal is to try to reduce the amount of acceleration that the egg experiences when it lands, because, as we know, acceleration is proportional to force. So if you want to make a softer landing, reduce the force on the egg, we need to reduce the acceleration it experiences when it hits the ground.
Our gravity has to be moved, right?
Yeah, we'll use Moon's gravity, which is like 1/6 of Earth, I think. Okay, any other questions before we generate some results? Okay. So to produce results, we use this button right here that looks like an XY graph. Click that and we can first choose a category. You can do forces, momentum, other quantities. For right now, we're going to do displacement, velocity, and acceleration. And then we choose a subcategory. The first thing I want to show you is the trace path. So I'll click on that. And what that's going to do, if I click on some feature, like say the edge of this foot, if I select that, say OK, what that does is simply draw a line that follows the path that that feature took. Okay? And let's go ahead.
Because it's not a single point, it's taking like the average of the curve of the radius.
I believe what it does is find the center point. So it's tracing the path of that center point. And one more time, displacement, trace path, choose the other leg, say OK. Okay, so now this allows us to see, we rewind that and replay it, we can see the precise path the egg took, or the feet took, once they hit the ground. In this case, it didn't bounce around too much, but like if we had the one where it bounced all the way off the landing pad, that would be a little bit more entertaining to see. Okay, so that's one result that we're interested in. The other result is to actually plot the acceleration as a function of time. So we go to the same results plots button, choose a category, it's still the displacement, velocity, and acceleration. A subcategory, we can do velocities or displacements or accelerations, and we can do linear or angular. We're going to do the linear acceleration, and then we'll select a result component, so you could do it in the X, Y, or Z direction, or we can do the overall magnitude. That's what we're interested in, is the magnitude of the linear acceleration, and then we need to choose an object or a face that we're computing this for. So I'm just going to click on the egg itself. Say OK. Okay, and that generates this plot, which shows, as a function of time here, it shows the magnitude of the acceleration that the egg experienced. So if we could make this bigger, you would see, if I had a better suspension, you wouldn't have this huge spike here, but you would see that it's got the acceleration of the moon here, and then it's a little bit lower acceleration after it lands and bounces around a little bit. But this huge spike right here is where the egg actually banged into the landing pad. And on this graph, we can actually, let's see if I can get this all to show up on the screen. So we can actually click and drag this cursor and see the red cursor on the graph and what the position of the egg is that corresponds to that particular time. So like here it hasn't, maybe I can just step through it down here. That just works too. Okay, so there's where it, well, right. Let me zoom in on the timeline here a bit so that I can get higher fidelity. Okay, so it hasn't hit the ground yet. Now, where's my graph go? There it is. Okay. Okay, so if I drag this timeline, now that I've zoomed in, I can get smaller time steps as I drag it. Okay, so you can see right there, right, that little jump in the acceleration graph, that's where the first leg hit the landing pad and it caused a slight jump in the acceleration, but then as we go to the next time step, that's when the egg itself hit, and that's what created this huge spike. So the question was asked a moment ago, can you get it to highlight if there's contact? I don't know of a way to do that, but what you can look for is a huge spike in your acceleration plot, and that would tell you if you actually had contact, an impact like that. So you can drag back and forth through the timeline to see, and you can right-click on this, and you can export all the data to a CSV file if you wanted to look at all the numbers in Excel or some other program like that, or if you wanted to plot it in a different way. You can do that. Okay, so do you have any questions about anything here? There's one, okay.
How do you get to show the plot again?
Okay, for the plot, you start by going to this results and plot button. You're going to choose a category, subcategory, and just fill out that box, and then that'll create the plot. Now once you've created it, it'll be down here in this feature manager of your motion study, and if you close the window, you can just go back to that plot in the feature manager. You can right click on it and you can say show plot, and it'll come back. So you don't have to keep recreating it. Okay. Yes?
If you recalculate the simulation, will it also change the plot and carry that data through? Or will
Yes, it will update the plot if we recalculate it. So, let's see. Let's do, we go back and modify one of the springs. Let's do spring 1. Okay, so let's give it 10 pounds spring constant. Let's do 0 damping. And okay, so it's going to be kind of hard to show all this on the screen at the same time, but we'll try. Okay, so let's recalculate. Well, it looks like it hit the plot. We'll open it and look at it again after it's done its calculation.
Self-adjusting.
If it rolls off the edge, it'll start falling.
It will. Okay, so here's our new plot. And okay, so backing up. Okay, so it comes down, it hits the ground. It appears that the egg does again hit the ground. Then going a little bit further, okay, it doesn't flip and land on its head right there. That's that spike right there. And then it slides and falls off the landing pad, and that spike right there is going to be when the egg hits the neck surface of the moon, and then it just goes on from there. So there's another big spike. Okay, yeah, that's when it again hit the surface of the moon. So anyway, the graph does update when you recalculate. Okay, any other questions? Okay, so what you're going to do for, what you're going to turn in for your homework is you're going to design your suspension so that it doesn't do any of this stuff. But then what you're going to turn in is actually just a screenshot of, I would just do the entire screen. So like using the snipping tool, you're going to do corner to corner, do a screenshot that shows the trace paths and also shows the acceleration curve on it, the XY plot. And what I've asked you to do is write on here the values of the spring constant and the damping constant that you use. So you can just use this little pen tool in the snipping tool, and you can just use it like Microsoft Paint. You can just literally write in there K equals 1 and C equals whatever you use. So just write it in there and then save this as a picture file, and that's what you would turn in for this part of the homework assignment. Okay, now the last thing I need to point out about this is purely rigid body motion. There's no deformation happening. The legs don't, like the components of the leg don't deform. The egg doesn't smash when it hits the surface of the moon. This is rigid body motion. What we do next week, we'll look at deformable bodies. Okay, so next we want to look at photo rendering. And we'll do that using this Corvette model, which again, you can download this from D2L. Okay, so in terms of graphics, there's really two popular methods of rendering, of generating an image of a computer model. One of those methods is called rasterizing. The other method is called ray tracing. Now, rasterizing is what you're used to looking at in the SolidWorks display window. The images we've been seeing have all been rasterized. That's also the graphics technique they use in video games. Call of Duty and stuff like that, they're all rasterized. You're essentially just taking the object and projecting it onto an image plane. That's all you're doing. The other method, ray tracing, is a lot more physically realistic. Because with ray tracing, what the computer does is shoot out rays of light, or shoots out vectors from a light source. And it lets those vectors reflect and refract and behave like actual rays of light. And they bounce around, and then some of them will come back to the viewport. And so you get a lot more physically realistic images using ray tracing. But it's a lot more computationally intensive. And I think trying to demonstrate this, we're actually going to stretch the limits of this laptop computer. So I hope it actually will work for us today. But again, another final exam question, so keep this in mind. Rasterizing produces lower quality images, but it's a lot faster. Ray tracing produces much more realistic, physically realistic images, but it's much more computationally intensive. Okay, so once we've turned on that photo view add-in, we now have this photo view 360 menu up at the top, and this is where we can define or create the image that we want. So first thing we want to do is turn on a preview window so that we can see what it's going to look like. If you do integrated preview, that's going to turn your whole display into a preview window. Your computer will get very angry with you if you try to do that. Just use a small preview window, and I really would keep it as small as possible. Preview window, and it's updating. I really would make that preview as small as possible just so it can update faster. Okay, so as we do things like zoom in on the model, it will update that in the preview window. Okay, so pause that for now. Back in the Photo View 360 window, there's a few of these that I want to point out, a few of these options. So if we go to the Options tab, tons of stuff in here that you can play around with if you want. I just want to point out some of the basic things. One thing to be aware of, this render quality lets you choose good, better, best, or maximum. That's affecting how many bounces the ray of light will take before it stops calculating. Okay? So if you do good, it's going to take relatively few bounces, and then it's just going to disappear. So if you ever have an image and it looks like there's a black hole in the image, that's because the ray of light is going in and it's taking a few bounces, but it's not bouncing enough to get back to your eye before it stops calculating. So in that case, you would need to increase the render quality. I'm going to choose better, because I think this computer can handle it, and I want it to at least look decent. But you can choose the preview render quality, that's for this, and then the final render quality, which is what you'll do at the end after you get your image defined the way you want. And you can choose the size of the output image that you're creating and the format that you want it saved in, JPEG or some other type of picture file. Okay. So those are some of the options to be aware of. Now, back in the menu, you've also got the Edit Scene tool, which lets us find an image and apply that as background instead of this faded gray background. There's lots of predefined images that you can browse for that are already loaded on SolidWorks. You know, courtyard. Let's see. I'm just going to do courtyard because I tried that one earlier and it worked okay. But I think somewhere in here, yeah, you can do kitchen. You can make it look like your Corvette is parked in the kitchen. You'll see reflections of the oven and the microwave in the headlights and stuff like that. It's pretty neat, but I'm just going to do, or you could take a picture, you could take your own picture of the library lawn, and you could have the Edmond Lowe Library reflecting off of the surface of the car. Anyway, I'm just going to do courtyard. Try that one. Okay. Yeah. Okay. Okay, so it applies that particular background image. Also, on the illumination tab, this lets you change how reflective the surfaces or the background are going to be, and you can set the rendering brightness so you can make it look kind of washed out or very sharp and clear. So you can play with the brightness and the reflectivity. I'm not going to try that now with my computer. Okay, now, okay, do you notice anything that looks a little bit off about this image that we've created so far? Yeah, you've got the shadow reflecting on the side, so your car looks like it's been parked on its side, and you can see down here in the graphic, you can see the reflection of the car is on the side. So we can fix that by going back to that edit scene. Okay, this. Go back to the edit scene, and there's a section here called floor, and you can choose where the floor should be aligned. In this case, I think we want it aligned with the XY plane. I'm going to choose that, and that fixes that problem. So the floor now looks like it's underneath the car, which is good. Okay, another thing we can control is what camera is actually taking this image, and what type of lens does it have. So we can go up here. Now this is in the view menu. You go to lights and cameras. You can choose this add camera option, and this opens up a new window. How's that? Come on. Okay, so in this new camera window, you can drag the camera around, and if I had this unpaused, you would see it update as I drag the camera. But what's important here is you can choose what type of lens this camera is using to produce this photographic image. So, like a telephoto lens, that's what they use like in sports, where the camera is really far away from the action, but it makes it look like it's closer, but the effect that has on the image is it flattens everything out, right? On the other hand, a wide-angle lens, like we can choose 24mm wide-angle lens, okay, that adds a whole lot more perspective to the image. Now, what is perspective? Like, does anyone remember from like junior high art class how we define perspective, or how to describe perspective? What is the perspective in an image? What effect does perspective have on the view? Someone give me an answer. Okay, it has to do with the way the view appears in the sense of what's the difference between things that are closer to you and further away. With perspective, something that's further away looks smaller than something that's up front, up close. And that's what we have trying to happen here, is with perspective, it's going to make your image look a lot cooler, frankly. Because it's going to look like you're right there in the action. Like the front of your car is going to be right in your face, and the back of the car looks smaller. Okay, so that's how you can add camera. I promise your lab computers will do a lot better job with this. Okay, let's put an end to this. Okay, I also want to show you how to add a spotlight or a directional light. Well, okay. You go to the view menu. There is where I chose to add camera. There's also options that let you put in a directional light, and you can specify the color of the light. You can specify drag it around just like I put the camera to put it in different positions. Okay, so lights and cameras. Add spotlight or add directional light. You can change its color to make it red. You can drag it around here to adjust where it is. You can choose whether or not it's going to have an effect on the photo view, so make sure you check that box. Say okay, otherwise it won't show up in your image. But now you can see the red tint to the wheels. That's the effect of the spotlight that I just added. Okay, well, the last thing for this then is, once you've set everything, the camera, the preview, the spotlight, you got the preview looking the way you want to do a final render, okay? Because this preview is going to be grainy and pixelated. You want to go up here to final render, and it's going to go through, and what this does is shoot a whole lot more rays of light at the object. So you get a much more a much better looking, better quality image. So it does take a while. Like on this laptop, this would probably take 20 or so minutes to go through, because it's going through multiple passes and refining the image each time. But let me just show you, if I can, the one that I did earlier. Okay. I'm going to give that a second and see if it will bring up the one I did earlier. But do you have any questions about anything that we've covered here from the photo rendering options?
Where was that final render button?
It's on the Photo View 360 menu. So with those other buttons that I was showing you, there's one called photo render. So it still has a lot of work to do, but you can see already this is looking a whole lot nicer than the images, the models that we're used to looking at in our SolidWorks graphics displays. This looks pretty cool, considering it was just a SolidWorks model, just like everything else we've done this semester. So, the assignment description is on each row. What you're going to do is create a photo rendered image, either of the Corvette, or you can choose some other model that we've done for homework this semester. Any model we've worked with this semester is okay. Don't just pick some random model from the internet, though. It has to be one we've worked with this semester. Okay, so if there's any questions, I'll be up here. Otherwise, have some fun with this. I hope you enjoy.